In this section, I want to talk a bit about the actual application of how you can use non-target analysis. And I want to give two examples of how we've used this approach in my laboratory at Johns Hopkins University. The first one is to assess chemicals that are present in e-cigarettes, both in e-cigarette liquids as well as aerosols. So these are the aerosols that individuals are actually inhaling. And the main goal really was to think about what are chemicals that are present in these systems, with the goal of thinking about what are potential health implications that are associated with these exposures. And so what we did for this is we analyzed 4 different e-cigarette products from 4 different companies, from Blue, from Juul, Salt, and Vuse. And we used a condensation device where we basically artificially simulated vaping to collect these aerosols. And then we were using liquid chromatography, high-resolution mass spectrometry to actually identify compounds of interest or the compounds that are present in these aerosols. And what we did is what is shown here also in this table is we analyzed the e-cigarette liquid. So that's the liquid that's basically in these e-cigarettes. And then we simulated 3 different intervals that had 100 puffs each, which are here indicated in this table as interval 1, 2, and 3. And then we monitored, or we looked for 2 different aspects. We, first of all, determined the mass of the aerosols that were produced during these intervals. And then we also looked using high-resolution mass spectrometry for how many compounds were actually detected. And what you can see here in this table is that, first of all, the masses of aerosols that were generated differed substantially. But most importantly, especially in the context of this lecture, we saw using high-resolution mass spectrometry, we were able to detect large numbers ranging from about 770 to more than 2,000 different compounds in these e-cigarette products. And you can also see that for some, such as this product Blue, which is the first one on the left side here, you see that we have the highest number actually in the e-liquid, whereas we have slightly smaller numbers in the aerosols, whereas for some of the other products, we see actually higher compound numbers in the aerosols compared to the e-liquids, which indicates that there are some compounds that might be degraded, or in other cases, some compounds that are actually being formed. And overall, what we were able to identify using high-resolution mass spectrometry is that some of the compounds that we were able to detect, especially in the aerosols, belong to a homologous series resulting from the decomposition of high molecular weight compounds during vaping. One important fraction that we were able to detect are so-called lipid-like compounds. So these are compounds that are in their chemical structure very similar to lipids. And this was important for us because these compounds have been associated with respiratory health effects. And we were also able to identify using reference, like unambiguously identify 6 compounds using reference standards. One that was very surprising for us was caffeine, which is a stimulant that was present in some of the aerosols, but we also detected things like plasticizers or flame retardants or certain flavorants that were present in these either e-liquids or aerosols. But one aspect to highlight is that despite the fact that we detected hundreds of these chemicals, most of these compounds remain unknown. And this is important to consider because that also means we don't really know the potential health implications of these chemicals that are present in these aerosols, which is something that still needs to be investigated further. A second example, and this is now going basically from the external exposure assessment into like the internal exposure assessment, meaning using biospecimen, a study that we did. In this example, we used non-target analysis to assess the exposures to previously unknown organic chemicals in hairdressers as a result of the many hair products that are being used in hair salons. And so what we did here was we analyzed urine samples from 23 female hairdressers, primarily serving ethnically diverse clienteles, and 17 female office workers, which we used as a control group. And similar to the example before, we also used liquid chromatography, high-resolution mass spectrometry here. In this case, we actually used a suspect screening. This list basically contained chemicals that were reported to be used in the hair salons using a questionnaire that was given to the hairdressers, as well as compounds that were previously reported in literature in different hair products. One aspect I wanted to highlight here is the pooled quality control sample. So what this means is that we basically used a subsample of each of the samples that were analyzed and mixed them together. And this was basically used to account for any background contamination and also determine chemicals that are present basically across all hairdressers. To talk a bit more about the aspect of how many compounds are initially detected and how many compounds are actually ultimately confirmed, or for which we have a good estimate of the chemical structure, I'm showing this table here. So with our high-resolution mass spectrometer, what we used, or a technique that detects both positive ions and negative ions. And so initially we detected, in all of these samples, we detected 11,200 compounds in positive mode and 16,600 samples in negative mode. Once we used background subtraction, so we basically compared the compounds that we detected with those in a blank sample, and we only looked for compounds that were present in our samples in at least 5-fold higher amounts than in our blank. You see that these numbers go slightly lower. So about 600 samples in positive mode and about 800 samples in negative mode were attributed to just background, basically. But then what we did is we used this pooled quality control, or QC correction, where we basically looked only for compounds that were present in all of the pooled QC samples. And in total, we analyzed 18 different samples. And then we also looked for the variability in the peak areas of these compounds that were detected, that had to meet certain criteria, which is indicated here as the relative standard deviation. Peak areas had to have a relative standard deviation, RSD, of lower than 50% in the original samples, and then lower than 30% after the correction. And I hope you can see here in this table that just by this quality control, the number of compounds that you detect or that you are confident that are coming from a sample is reduced drastically to about 1,350 in positive mode and 1,070 in negative mode. In addition, we were also then interested in for which compounds do we actually have information about the fragmentation, so these MS2 spectra. So in positive mode, in this case, we had information on 1,117 compounds and about 750 in negative mode. And then, because we were interested in primarily exposures in hairdressers, we also used a peak area ratio where we basically compared the abundance, the peak area in the samples from the hairdressers to those of the office workers, which we used as a control group. You can see this further reduced the number to around 470 positive mode and 330 in negative mode. All of these compounds were then compared to our suspect screening list, so the list that we had compiled based on the hair products that are used in these hair salons, which further narrowed down the number to 141 in positive mode and 129 in negative mode. And after manual quality review among these compounds, which, for example, accounted for the peak quality, we ended up with 38 compounds that we had a very high confidence in about the detection in positive mode and 28 in negative mode. So I hope this illustrates both the importance of this quality control, but also how, despite this initial detection of more than 10 or 15,000 features in the samples, you really end up only with a much smaller number of compounds that is likely to be, in this case, separate from or distinguished from the control group. And also here, we were able to identify certain compounds. So parabens were one of the main contributors. So these are preservatives that are used in different cosmetics or personal care products. So we found, for example, methylparaben, ethylparaben, and propylparaben. And I think this was for us a nice confirmation because these compounds had been detected in hairdressers before. So on the one hand, this result wasn't surprising, but because we used the suspect screening list, this was for us a good way of basically showing that this approach can really be used to identify exposures to certain chemicals. But again, similar to the previous example, the main aspect also here is to highlight is that despite all these efforts on the large number of chemicals that were detected, the identity of the majority of these compounds still remains unknown. And this is really one of the challenges that we're still dealing with non-target analysis. And the main reason is that we're relying on the comparison with online databases that are not very extensive to date. So hopefully this will change in the future by having more and more compounds that are present or that are entered into these databases that can really help identify these compounds. One aspect that I think is also important to consider, especially thinking about, okay, which are the chemicals that we have to worry about, is that, thinking more about, okay, what does this actually mean in terms of the actual risk? So I hope I was able to demonstrate to you that non-target analysis is a very powerful tool that allows us to identify large numbers of previously unknown contaminants in environmental samples or also in biospecimen. But the challenge with this is that it doesn't really allow or provide any information about the toxicity of the compounds. So it is unknown about, or we are unclear about, okay, what are the actual health risks that arise from these exposures? And when we think about also that ultimately, if we want to identify compounds, we need to buy reference standards, which are typically very, very expensive. The question also here is like, what other approaches can we really use to think about, okay, what are the compounds that are likely to be of concern, and for which we then buy reference standards, both to confirm the identity, but also to determine the concentrations, which is the critical step to do an actual risk assessment. And one thing that I want to highlight here that we've been using our online databases and computational toxicology approaches, such as the CompTox chemical dashboard that has been developed by the US Environmental Protection Agency, that can be used to assess the toxicity of the detected compounds. Even if we don't know the exact chemical structure, we can basically enter the proposed or the tentative chemical structure, and this database basically gives you information about what are the potential toxicities, either because there is actually experimental toxicity values that has been reported for the specific compound, or what this online database also can do is so-called read-across predictions, which means that we are comparing the chemical structure with other compounds that are present in the database and basically determine similarities to then get a prediction of what a toxicity might be. And just to put this in the context, which is shown here in this graph, where you have basically non-target analysis, and then you have this online database matching, where you look for, okay, what are chemicals that have been reported before? And you can combine this then with this computational toxicity assessment, as well as with potential computational exposure assessment, to then prioritize those compounds that might be of highest concern. And this is important because based on these prioritization, you can then use these smaller number of compounds to then do a target analysis to quantify the concentration of these compounds, but potentially also to do more extensive toxicity testing, if that isn't available yet, to actually think about what is the actual toxicity of these compounds. I want to briefly talk a bit more about the CompTox chemicals dashboard, because I really believe this is a very powerful tool that can help a lot in kind of like prioritizing compounds. So this CompTox chemical dashboard is a very extensive database that has information about the physical chemical properties, the environmental fate and transport, exposure, usage, as well as toxicity of different chemicals. And at this point, there's more than 1 million chemicals that are entered in this database. I already talked about that it also allows for generalized read across, that this tool allows you to predict the toxicity of chemicals for which no experimental or model toxicity information is available, which is very helpful to just get a sense of is this a compound of potential concern or not. And again, this is very powerful because if you combine this with non-target analysis, this can really help to prioritize chemicals that are of highest concern and that need to be further prioritized. In summary, I hope in this lecture I was able to demonstrate that non-target analysis, or NTA, is a very powerful tool that allows us to detect previously unknown organic contaminants in different environmental media as well as in biospecimen. Despite all the advantages, one of the main challenges that remains is really this identification of the detected chemicals. And this is currently limited by the compounds that are entered in online compound databases, because this is the critical aspect that we need to compare our results to, especially because reference standards of chemicals are very expensive. And as I alluded on at the end, the other aspect to think about is that non-target analysis alone provides a lot of information about chemicals, but it does not provide any information about the concentration of the detected compounds, which is an important aspect when we think about the risk assessment, because ultimately, the dose makes the poison. So if you really want to do a risk assessment, you need to determine also the concentration, where you need a reference standard for. And again, this is why prioritization is so important. And what we've been pursuing is the combination of the computational exposure and toxicity assessment to help us with the prioritization of these compounds.